Let's take a look at bond lengths and angles and predict the shapes of molecules. As you might predict, single bonds are the longest bonds. They're also the weakest bonds. Go to a double and then a triple bond, things get stronger and shorter. So a triple bond would be the shortest and the strongest type of bond. So this gives you a nice relative idea of bond strength and bond length. How will these things arrange themselves in order to form a shape? Well, it's all based on the idea that the electron cloud will try to stay as far away from another electron cloud as possible. So if you have an AB2 system, in other words, a central atom with two things on either side, it'll go linear. It'll try to get as far apart as possible. The bond angle will be 180 degrees. If you have a three-petaled flower, if you will, that's where you have an AB3 system. And these three things, the furthest they can get away in 3 dimensions is still flat, a trigonal planar shape with 120 bond angles. Now it's possible in a system like this you could have a lone pair instead of a third substituent. And that lone pair will occupy space, and it will bring the angle down to about 180 degrees. We would call that bent. If you have 4 substituents, a 4-petaled flower, now you have to think in 3 dimensions. The furthest these things can get away from each other is in a tetrahedral shape. The bond angles are 109.5 degrees. If one of the petals is instead a lone pair of electrons, like NH3 for example, that will occupy a little more space than the atom itself, and therefore it'll push things down to about 107 degrees. They call this trigonal pyramidal. And if you have 2 lone pairs, like the case of water, the bond angle could go down another couple degrees to a bent shape, 105 degrees. And mostly we're concerned with the angles, but we might as well talk about the shape as well. If it's a B5 system in 3 dimensions, that's a trigonal bipyramid. The landing pad here, and I think this really doesn't look as triangular as it should, would give you the 120 bond angles, 120 degree bond angles, and right there would be the 90-degree bond angles. You'd see both of them. Now, whenever you replace the substituents, the lone pairs, take them off the landing pad. I think of this thing as some kind of satellite, and I call that the landing pad. That's the top, that's the bottom. Can you see it? That's your flat triangle right there. It shows up much better there. There's your landing pad. Take one off the landing pad, and now it's called either a seesaw or what did they call it? There's another name for it. Seesaw is fine. And that's the shape there. Take off 2, and it now becomes 90 degrees T-shaped. There should be another substituent down there as the bottom part of the T. And on the landing pad is completely gone. It's now linear. That would be 5 substituents, but 3 of them are lone pairs. That's a linear shape. Octahedral is another symmetrical structure, and in this case, all the bond angles are 90 degrees. Once again, we take off from the landing pad for the lone pairs, giving us this square pyramidal shape. You might want to rotate that down to see that. 2 lone pairs, square planar. 3 lone pairs, T-shaped. We've seen that before right there. And all 4 lone pairs then goes linear. And bond angle is 180 degrees. In all 3 cases here, the bond angle is 90 degrees. That's bond lengths and bond angles.